All right, today we'll look at a critical analysis of self-supervision, or what we can learn from a single image, by Yuki M. Asano, Christian Ruprecht, and Andrea Vedaldi. This paper, I really was excited when I saw this paper because the outset is so cool and the experiments are very promising. So we'll take a look. Basically we show that 3 different and representative methods, ByGAN, RotNet, and Deep Cluster, so this is self-supervision techniques, can learn the first few layers of a convolutional network from a single image, as well as using millions of images and manual labels, provided that strong data augmentation is used. However, for deeper layers, the gap with manual supervision cannot be closed, even if millions of unlabeled images are used for training. We conclude that, first, the weights of the early layers of deep networks contain limited information about the statistics of natural images, that second, such low-level statistics can be learned through self-supervision just as well as through strong supervision, and that 3, the low-level statistics can be captured via synthetic transformations instead of using large image dataset. Okay, so as I said, I was kind of excited when I saw this, and what they're talking about is self-supervision. So really quickly, for those who don't know, self-supervision is a technique where if you have images but no labels and you would still like to learn something from them, you can do a pre-training step for your network. So basically you have your neural network, F, and what you would like to do is you would like f of x to be close to y for x and y in your training data set. But you can, if you have a much larger data set of just x's, right? Here you have pairs of x and y of just x that are sort of similar to the x in your labeled data set. You can kind of get your network used to the data by doing this self-supervision. So what you would do is you would sort of come up with your own labels for the data points. And one way is this. We'll take just this RotNet as an example. So what you'll do is you'll input an image. So maybe an image of the number 3 in handwritten digit recognition, but you flip it. You flip it to its side, right? So it's the number 3 right here. And then you ask the network to come up with an answer. Is it upright? Is it flipped to the right? Is it flipped to the left? Or is it turned on its head? Which one is it? And of course, you who did the transformation know the correct label, right? So this is how you come up with sort of fake labels for your data. And this works surprisingly well. And what this paper basically says is that you do not actually need this giant database here. It's actually sufficient sometimes if you have one single image where you do this on. Now, the claim is a bit of a cheat, I have to say. But we'll go into that. And further they say, okay, it's enough to have one single images to learn the features of the lower layers of the neural network, because they usually tend to extract low-level features that you can learn from a single image, but the higher level features, you really need the supervised data set. It's not enough to have these self-supervision techniques. And even if you have many self-supervision samples, so if you actually do have this giant data set, it still doesn't help you for the higher layers. It almost calls into question this you have a giant data set of unlabeled things notion that is often presented, including by me. Okay, so what do? They take either single images or just very few images. So they also have a setting where they take 10 images. For the single image, they hand select it. So they hand select the following 3 images. So this image right here, they select because it's very crowded. There's a lot going on, right? There's people, there's objects, there's lighting, and so on. There's houses, these lines, there's perspective. So that's why they select image A. Image B here, they also experiment with image B, is a drawn image. As you can see, there's also lots of stuff going on, but they basically want to research how does a natural image compare to a artificial image. And then in C, they have this as sort of a control, because there's lots of parts here where there's not much going on compared to here. In most of the image, there's lots of stuff going on. And this image on the image number C, or letter C, has large areas where there's nothing going on. Okay, so these are the single images. Now, why I say it's a bit of a cheat is that these images are actually super large. For ImageNet and for C410, this might be one of the samples of the C410 or ImageNet classifier. Now, of course, C410 is a lot smaller than ImageNet, but still for ImageNet, these are, there are many pictures here, not just one. So to say this is from a single image, it's technically true, but then if you split it into multiple images, it's technically not true. So it would have been fun to see what actually happens with a single image when you downscale it. But okay, so how do they investigate this? They have this 5-layer neural network right here. So this 5 convolutional, I'm going to guess there's 5 convolutional layer. After each convolutional layer, I think there is some batch norm and ReLU, and then to the next convolutional layer, and so on. And then at the end, maybe there's also some pooling here, max pool. At the end, there is going to be some linear classifier that classifies it into either a 10 or 100 or 1,000 classes, whatever you want. The way they investigate this is through linear probes, so-called. Now, linear probes are somewhat of a technique to inspect how much each of the layers learn. So if we again draw our network right here, and this is the input X, right? So you have the hidden representation 1, hidden representation 2, hidden representation 3, and here you output it to the Y hat. And that you compare with the Y from your data set, right? The X is from your data set and the Y is from your data set. Now, linear probe wants to investigate how useful a given hidden representation is to classify the output. So what a linear probe would do is it would take the hidden representation here and learn one single linear classifier to classify that hidden representation to come up with a Y hat given H1 or something like this. So the important part here is that this is linear, right? This is a linear classifier. You do nothing more. You take the representation, and instead of this entire giant neural network on top of it, you simply build a linear classifier. And you can build these linear probes from any layer right here. You can build a linear classifier on top of this, on top of this. And then you basically look, how good is your linear classifier when trained on that hidden representation that the network comes up with. And that's how you estimate how much information about the target, or let's say how optimal the representation already is. Because at the end of the network, right, you do have a linear classifier. So at some point, this representation must go into a form where it is now linearly well classifiable. And the assumption is basically that these layers of the neural network successively make a representation that is more and more linearly classifiable. And that is a strong assumption, right? And this paper here uses linear probes exclusively. And that is a bit worrisome to me, because I have my troubles with this linear probe approach, because this strong assumption that more linearly classifiable is better, it just rubs me in the wrong way, right? We know that the information content can never increase from layer to layer about the label. So any information about the label that is in H1, that is in H2 must also have been present in H1. So technically, if we just built the correct classifier, we could predict from H1 just as well as from H2, right? Because we're actually doing it. We're building the neural network. But the fact that we cannot predict linearly as well using H1, so the fact that this classifier here performs worse than this classifier here, because H1 is a less optimal representation in a linear sense. It's just, and the fact that, I mean, yes, but then to use that and to estimate, oh, how useful is a representation? You're equating usefulness with linearly classifiable. And that I disagree. A representation can be extremely useful if the following layers manage to do something useful with it. And that can be something completely different, or it can even be the opposite of the linear classifiability, right? So this is kind of my problem here, and they don't do a good work of convincing me otherwise. So they don't employ different techniques other than these linear probes. In any case, when they do this linear probe, you can see right here that the percent supervised performance, so that's how much percent of supervised performance do you get. So single image self-supervision. We show that several self-supervision methods can be used to train the first few layers of a deep neural network using a single training image, such as this image A, B, or even C, provided that sufficient data augmentation is used. So what they do here is they use this self-supervision, then they take the signal from the convolutional layer 1, the hidden representation, that's H1 right here. They train this linear probe on it, and they see how well does it perform after. And this is after the network has been self-supervised with RotNet, for example. And then they compare that to the linear probe at layer 1 of the supervised network, right? So you take the supervised network and you do the same thing. And there they find, okay, this RotNet and all the other techniques, they perform very well. And especially if you only do a single image, they perform better, as you can see right here. I mean, if I interpret this correctly, this one RotNet, one BiGAN, one deep cluster, these are these top things right here. And the 100 is the comparison to the supervised performance, right? So 100 means 100% of the performance of the supervised representation. This is absolutely crazy to me. And this, in fact, so let's just interpret it from their perspective, right? So you also have random. So if you randomly initialize a network, then with training a linear classifier on the hidden representation 1, you could reach something like 60% accuracy, which is impressive. Okay. But if you do the linear probe at layer 2, you reach a lower accuracy. Now, remember, this is lower accuracy compared to the supervised performance, right? So there are two effects at play here. The supervised performance is going to go up because if you believe the assumption that the successive layers make the representation more and more linearly classifiable. But also it could be that just at the same time, the self-supervised performance, the performance of the self-supervised representation is going down. So the graph here is sort of, I don't really know how to interpret it. And it really goes down after that. That's why they say you can learn the first layers fairly well with self-supervision, even from a single image, but you cannot learn the upper layers. And they're basically just measuring this using this linear probe method compared to the supervised performance. What I would somewhat like to see is that let's say you train a self-supervised network, fine, but then you freeze this layer, and then you fine-tune the rest of your network on top of that representation. That would actually give you an estimate of how useful is that representation if I had an all-powerful function approximator, which is a neural network. And then, of course, you're probably not going to get supervised performance. And by the way, you'd have to compare that also to supervised with and without pre-training using self-supervision. And then you actually get a good estimate of what kind of a representation do these things learn. In this case, all we get out of this is this linear probe thing compared to the supervised representation. And it just seems a bit uninterpretable, honestly. And the fact that here you can go beyond 100%, you can actually be better than supervised, should already tell you that this linear probe thing might not be a good instrument, might not be such a good instrument, especially in the lower layers. The lower layers will be most inaccurate with these linear probe measurement. But that's their finding, basically. They can learn the features of the lower layers as well in terms of this linear probe formulation as the supervised learning. Again, they never compare this to fine-tuning on top of these representation or compare it to self-supervision plus supervision, which I would really expect. All right. So they say they do lots and lots of data augmentation. Since, of course, they only have a single image, they basically supercharge data augmentation, and they show that this helps. Now, I don't want to actually go into the very details of what they're doing, because they just have different methods of augmentation. They just have different networks, but here are the results. So if this is on ImageNet, if we use full supervision, we use the entire data set, and we do this linear probe evaluation, we get a 20% accuracy after layer 1, a 36 after layer 2, and so on. This goes up as we go through the layer. So this kind of gives credence to the hypothesis that these layers sort of make the representation more linear. And then they have a bunch of scattering and random networks, and k-means pre-training, which doesn't get you a lot, but that's what they compare it to, basically the self-supervision to just the scattering transforms and things like that. But then they get into their methods, and here we'll look at, for example, this ROTNet. So if you train on just one image, this image A, of course, if you have one image, then you get this much of the layer 1. Now, okay, so now that I see this, here they have this column right here, which uses the full data set. What I think this is the self-supervised training using this many images. So what if you do ROTNet self-supervision on this many? It could also be the performance after supervised training, after pre-training with this method. But I think it is the performance just after self-supervision, again, with no fine-tuning on top. And then evaluating these linear probes. That's why this number is lower than this number right here. But astonishingly, after you do it with just one image, you get a higher number. And if you do it with 1,000 images, you get an even higher number. But if you do it with many more images, you somehow don't get a higher number. This all seems a bit weird, honestly. It basically means that, okay, it is more important to augment the same thing over and over and over in different ways than it is to incorporate different images. I mean, there's ways I can believe that, but I'm not sure. But you basically see that after a while, the performance compared to the, first of all, to the supervised method. So yes, if you look, for example, here, up here, drops dramatically. And even if you have the full, now I'm convinced that this is just self-supervision using the full data set. Even if you have the full data set, but only do self-supervision, your performance still suffers compared to the supervised training. Right? So that's why they have these two claims. You can learn the first layer representations fairly well with self-supervision. That's comparing this number to this number. You can do so even from a single image. That's comparing this number to this number, right? And noticing that it's almost the same. These two numbers are almost the same. Actually, one is a bit higher. You can learn that fairly well, but if you go down the layers, you will basically suffer with your single image and with your full image self-supervision. So you need the supervised signal to learn the features of these later layers. And that's all evaluated with these linear probe things. Yeah. So that is their main claims right here. And they kind of analyze image A and image B. So they come to the conclusion that image A works much better because it's natural, and image B is not working so well, but this depends on the self-supervision used. And image C still apparently works quite well, even though it has these large areas of nothing, which all of this is a bit weird, but it's definitely cool to see these results. Now, again, I would like to see something like you freeze these representations and then you actually train a neural network on top of that and look how that performs. That would actually be an interesting thing, though. Maybe they've done this and I'm just unaware right here. They look at the filters that these methods have learned just from self-supervision on a single image, and you can see these are the types of filters that we would see using even supervised learning. If you look at the filters, they turn out to look pretty much like this. Of course, I can't decide if these particular things are good or bad filters or not. They do some qualitative analysis, and here they have fine-tuning. Okay. Fine-tuning experiments. The pre-trained model's first two convolutions are left frozen or replaced by the scattering transform, and the network is retrained using ImageNet training set. Okay. Here we go. So if you do this fully supervised, you get to a 59.4. Now, okay. This seems very low accuracy, honestly, for even like for ImageNet, but maybe this is their thing. But if they do this on top of these self-supervised methods, they do get a fairly good, they get a fairly good accuracy right here. I would have liked to have this evaluation right here be applied in the table above and not these linear probes. They just seem kind of wonky. But you can see that it is possible to learn this using just a single image, to learn the features of the lower layers. Now, how you exactly would put this into a training procedure, how you exactly make use of this during training, if you already know that it's not going to help for the deeper layers, I'm not so sure, because at least you always have your own data set, right? So you always have at least that many images that you can self-supervise train on. But it's certainly interesting results. And with that, I think I'm going to leave it at that. And thanks for listening. I hope you enjoyed this. And bye-bye.